demodulation. Then we identified the three main properties of the carrier onto which we can load the information. That was amplitude, frequency, and the pace. Accordingly, we had amplitude modulation, frequency modulation, and pace modulation as three major types of analog modulations. In fact, all modulated signals are analog. The difference between the two names, analog modulations and digital modulations, come mainly because of the input to the modulator. If the input to the modulator is a digital signal, we call it a digital modulation technique. If it is an analog signal, we call it an analog modulation technique. However, output is always let me mute some of you. Okay, so whether it's digital modulation or analog modulation, output is analog carrier, right? So it's a kind of a conversion from an input signal which contains information content to an output signal in which that information content is loaded to a carrier. And we learned why we need a carrier. There were several reasons. And then we started to discuss AM and its derivatives. Under AM, we discussed the very basic concept called single-tone AM. And that idea we extended or extrapolated for two-tone and then three-tone, likewise, a multi-tone signal. And finally, from multi-tone to a practical modulating signal such as audio or video. Okay? That we call the generalized AM signal, the final one, which is related to a signal, practical signal like XT, which can take any kind of variation. However, we assume that that XT modulating signal is having an average value 0. Then we discussed how the AM can be demodulated using two methods. What were the two methods? The most simple one we called envelope detector method, where it's basically a rectifier followed by a filter. Right? So that the envelope of the waveform will be recovered, but the selection of the RC time constant in the filter was critical, because if we find that RC is too much, then there is one error where we will be missing the negative sides of the waveform. And if the RC is too small, there will be a lot of ripple in the envelope of the waveform, output waveform. So within certain limits, we'll have to select the time constant of the RC filter in our demodulator. However, we learned another method, which we call the coherent detection principle, or there is another name for that. Some books call it synchronous detection. Okay. Still certain, some of you are in the waiting room. I'm sorry, let me admit all of them. I forgot the recording also. Okay.
Recording in progress.
Right, thanks for informing. I think all are admitted now, right? Yeah. Okay, so two demodulation principles. Envelope detection is one method. Coherent detection is the other method. Alternative name to the coherent detection, synchronous detection. And the diagram we have on screen is synchronous detection applied to what we call heterodyne receiver principle. This idea is that the signal on air is picked up and multiplied with a local oscillator signal. Let's call the signal coming in. We want to pick up the carrier FC. And this is FLO, local oscillator frequency. The output here will be, let's say, F out. That will be the difference between FLO and FC. And we make sure that this difference is our baseband signal. Baseband frequencies from 0 with a bandwidth of, say, W. In this case, it's audio in this example. So the audio bandwidth will be directly coming out to audio amplifier, amplified and played. And on air, we have different channels here. And AM channels, if I draw like letter M here, there will be carriers like this, upper sideband and lower sideband on each carrier. So if FC is this channel that you want to tune to, these other two channels, this one and this one, are known as adjacent channels. Adjacent channels in the spectrum. So remember that word, adjacent channels. One on the upper side, upper adjacent channel, other one lower side, lower adjacent channel. And these adjacent channels will have to be rejected because when you down convert, if any portion of these adjacent channels here, certain portions on these sides are also creeping through to the audio amplifier, we will get an interference. What do we call that interference? It is called adjacent channel interference. You hear certain noise due to frequency components of the adjacent channel. One way to minimize this is to keep a guard band between adjacent channels so that when planning spectrum, usually a small gap here in this place is kept as, we call it the guard band. Guard band. So even if the guard band is there, if your filtering or demodulation is not good, still adjacent channel frequency components can creep through to your audio amplifier, causing interference known as the adjacent channel interference, right? And if I want to tune to next channel, suppose I don't want this, I want to take this channel, then I want to increase the local oscillator frequency as well. So if I want to change the carrier frequency to a higher value, my local oscillator frequency also should change along with it, so that we use couple tuning, which is called gang tuning. So that tuning capacitors on the amplifier and filter, this is called RF amplifier and filter. Tuning capacitor in the local oscillator, they are coupled together or gang together so that they will tune simultaneously when you tune from one channel to another. Okay, so that's heterodyne in principle. You are mixing RF with the local oscillator in order to get the demodulated signal directly. These are the problems. Adjacent channel interference happens usually in this method because the filters you use in audio amplifiers are not that sharp. The filters have kind of a roll off like this. When the frequency is low, you can't get very sharp edges. Therefore, adjacent channel interference usually occur in this method. Okay. Another issue is that when you tune to the upper frequency, suppose you take a certain band, like a radio band here, when you are tuning to these channels, upper channels in the frequency band, your bandwidth will become wider. So more adjacent channel interference will be there for upper channels in the band, less adjacent channel interference for the lower bands in the lower channels in the band, which means that within the band, the adjacent channel interference is not uniform. Upper channels of the band will get more adjacent channel interference because of the wider bandwidth. Lower channels of the band get less adjacent channel interference. So it's not uniform treatment to different channels when you tune to them. Okay. Please voice or type if you have anything to ask or anything to discuss. Okay, I have one question. Can you explain further about the AM heterodyne using frequency spectrum and how they transfer the frequencies in the separate components in the model? How they transfer the frequencies in the separate components in the model. Could be if I explain with a triangle, maybe easier, right? Assume that you take this channel and you have this carrier, USB, LSB here. And if you take any particular frequency here, let us say fx, right? It will have a gap of fx from fc, and you will be tuning your local oscillator also to together with fc. Local oscillator will vary. Right? So in this case, your local oscillator is also tuned to fc. Right? So what is coming out is the difference between this. If I'm taking one frequency, as you said, take fx. What you are getting here is fx minus fc. The difference between this frequency and local oscillator, which is now tuned to the carrier. So that difference is directly an audio frequency, which is fx. Right? So, sorry. Fx minus fc is directly an audio frequency. Hope it is clear. So that depending on how far away your frequency is, you will have audio high frequencies here. So the audio, this band will be finally mapped onto an audio band starting from 0. Let us say F max. So that will be directly the audio signal. Hope it is clear. So how does the bandwidth increase at upper channels? What does that mean? Well, that is because you are tuning, right? when you tune an amplifier, let's say your pass band of the amplifier is B, right? Pass band of the amplifier is B, right? And so it could be a filter. I'm talking about this section now, RF section, right? It could be a filter having a bandwidth of B at a particular radio frequency. It has F1. So you are tuning to channel 1. Same circuit, the same circuit, when you change this capacitor, this is expected to be shifting to a different tune frequency. However, you will notice that your bandwidth become wider. So you are now tuned to F2, but your bandwidth is B dash, which is higher than B. So that is a problem with these tuned amplifiers, right? When you sweep your tuning, by changing the capacitor, your bandwidth becomes slightly wider. So the problem is actually here in the RF section tuning circuit. That's why in the high channels in the band, you get more adjacent channel interference. Okay, hope it is clear. Another question, why do the upper channels have a wider bandwidth? Why aren't all channels made to have the same bandwidth? All channels are having the same bandwidth here in the sky, right? Here in the broadcast, all channels have the same bandwidth. But what comes after this, after the RF amplifier, the bandwidth is varying because of the RF amplifier tuning, as I mentioned here. So when you sweep a tuned amplifier over a frequency range like this, your bandwidth does not remain constant. Some more in the waiting room, let me admit them also. Okay. Okay, so you can see our ideal expectation is to have the same bandwidth or same treatment for each of the channels on air. However, due to practical tuning issues, we have given slightly different treatment to different channels on air. So all of them will not be received with the same quality. One more question, is there any frequency shift in the RF? Yes, RF channel, RF tuning is shifting. If there is the shift, what amount it shifts? If not, why there is a capacitor? Yes, it is shifting from channel to channel here. Right? On air, you have multiple channels. So by tuning the capacitor, you are tuning to the next channel. From one channel to the next channel. Can you remember the manual tuning radios where you are rotating a knob like this? So that the capacitor will be changing here and you will be listening to the next channel in a moment. In between channels, you will hear some kind of noise. Right? In manual tuning, I'm sure you remember. So capacitor is there for that tuning. Right? And one more question, can you explain how tuning has to be done, both RF and local oscillator, in order to take baseband? They are tuned simultaneously. It's like something like this, two tuned circuits. Let me draw. Assume that you have one tuned circuit here with an inductor and a capacitor as the load of the RF amplifier. And you have another tuned circuit here tuned to the local oscillator, which is also FC here at the moment. And if you use a big capacitor, which is divided into two halves, you may remember those old capacitors. In old days, you have capacitors like this. Mechanical construction is that they have a rotary knob kind of thing here. And one set of plates are there. Another set of plates are coming out of this when you tune. And this is in two portions, one half and one half. This half is in the local oscillator here, RF section here. This other half, that's here. The other half is connected to the local oscillator here, and these two are gang tuned. So they are coupled by this rotary knob, mechanically coupled within the capacitor. So when you rotate the knob, you are tuning both capacitors simultaneously. I'm sure you have seen this kind of capacitors. Nowadays, they are very small. They are made using kind of plastics. So they are more compact than those old radios. Right? And also you will notice today, this tuning is done by using frequency synthesizers digitally. So you may not see this kind of capacitors anymore. Right? But I just drew this because understanding that will be easier here. So this tune circuit will be here in the RF section. This tune circuit will be in the local oscillator section. This is called gang tuning, where two tune circuits are simultaneously tuned using one common control. Okay. Another question, so this receiver does not have an image frequency, right? Yes, this one does not have an image. That image issue will come only when you have an intermediate frequency, which is that kind of a receiver is what we are going to study next. That's called the super heterodyne receiver. At the moment, we are studying heterodyne. They don't have this image channel issue. The issue with this one is the adjacent channel problem. So what is the job of local oscillator? Is it to bring the band pass frequencies to the baseband? Yes, exactly. Band pass frequencies are brought back down to the baseband frequencies due to this subtraction of FLO minus FC. The input frequency is subtracted from LO so that it's brought down into the baseband value. Right, so we now know the problem with the heterodyne, that is adjacent channel interference issue becomes serious, and quality of the received signal for different RF channels it's different. Therefore, we are not having the same quality for different channels in the tuning band. For this reason, heterodyne receivers are not that popular, because a user would like to have same kind of signal noise ratio, same kind of quality for all the channels he tuned to. Sita is asking, mixer is subtracting, right? Yes, you are correct. Mixers are there. Some of the mixers are adding, some of them are subtracting, but in this one, it is subtracting. Mixer will normally produce two outputs, out of which we are taking the subtraction here. Okay. Right, then we will look at an improvement to this, as one of you mentioned, the other type, super heterodyne. where our problem here was that the gain of the RF amplifier was varying. When you tune from one channel to another within the band, low, bandwidth is low. Upper channels, gain is high, bandwidth is high, bandwidth is wide. Likewise, so the bandwidth will become wider for upper channels when you tune over a band like this. Gain also you will notice initially low, gain also increases. Okay. So that's the problem with this kind of an amplifier. So our treatment to different channels is not fair. We are giving different gains and also different bandwidths while we tune from one channel to another. This can be overcome by putting what we call intermediate frequency section between this audio amplifier, audio section and the RF side. This part is radio frequency. This part is audio frequency. And we are going to include another set of circuits here, which are called intermediate frequency between RF and AF. Then we call it super heterodyne receiver. These principles of heterodyne and super heterodyne are not limited to AM. Even for FM radios, the ideas we are discussing here are used. Heterodyne idea, super heterodyne idea, they are used in FM also, FM receivers also, right? So this now includes that IF section. So you have three areas now, RF, IF, and this is AF. This time our purpose of our RF amplifier is to give initial gain, not very high gain, initially required gain to drive the mixer. But most of the gain to the signal is now given by the IF. So IF is designed to have a constant gain and constant bandwidth. So most of the gain to the signal is given there, not in the RF section, because RF section has variable gain and variable bandwidth. IF, we are not going to tune, no tuning here, it's fixed frequency section, this one. This part, this is the demodulator. After that, this is the AF section that also we are not going to tune. So gang tuning is still being employed at the front end like this. After the gang tuning, we get the subtraction output from the mixer, not the summation. So it will be FLO minus FC. And that is to be a constant, irrespective of the RF channel you are tuning to. So whatever the RF channel, it could be F1 channel or F2 channel or F3 channel from the air, irrespective of what channel you are tuning to, your intermediate frequency is fixed. What are the typical intermediate frequencies in radios? One common value is 455 kilohertz. It's a very popular intermediate frequency for low bands. And then for FM kind of things, we have 10.7 megahertz. Then for TV, we have 35 mega. Likewise, these are standard values in the world selected for IF, selected for intermediate frequency. Why they are standard? Because they are constants, irrespective of what RF channel you want to listen to. Because the frequency coming here is a constant, bandwidth of this amplifier will remain constant, and gain also will remain constant. So we are giving nearly identical treatments to all the channels that we are tuning to. So this is the way we overcome that earlier problem. Then this difference should be equal to Fi, and there are two ways that can happen. Either you can select local oscillator to be tuning above the carrier frequency, then we call it high tuning. If your local oscillator is carrier frequency plus Fi, we call it high tuning radio. If your local oscillator is below the carrier frequency, difference still remaining at Fi, then we call that kind of a design low tuning radio. So is it clear what is meant by high tuning and low tuning? If your local oscillator is above the RF channels you tune to, it's high tuning radio. If your local oscillator remains below the RF frequencies you tune to, it's a low tuning radio. So two different designs are there. Here, plus sign is corresponding to high, minus sign is corresponding to low. So the designer can choose high tuning or low tuning in his design. Now, we have another issue, although we have solved the adjacent channel issue now, because this IF section will have sharp cutoff, and only the wanted channel will go through it. This will have very sharp cutoff, and it will have constant gain. So adjacent channel issue will be solved. However, we have created a new issue, which is called image channel interference. That is image. As you can see here, assume that you are tuning your radio to a channel called channel frequency FC. This is what you wanted to listen or wanted to receive. And corresponding to this, you have, if you have another frequency in the air, given by this equation, FC plus 2Fi, FC plus or minus 2Fi, then we call it image channel. What will happen? Just think FC plus 2Fi is coming this way, and your local oscillator is FC plus Fi. I'm considering a high tuning radio in this example. So FC plus 2Fi coming this way, FC plus Fi as the local oscillator coming this way, your difference is still Fi. So in addition to the wanted channel, this image channel, unwanted channel, will also go through the IF section. This is unwanted, right? If it is on air, being radiated by some other user or broadcaster, it will also create the same IF, and our radio will not be able to discriminate between wanted carrier and unwanted image. Both of them will be received simultaneously, causing image channel interference. For a low tuning design, your image channel will be minus here, FC minus 2Fi. For a high tuning radio, your image channel frequency will be FC plus 2Fi. So you use plus for high tuning radios, you use minus for low tuning radios. Right? So though we received we have solved the adjacent channel interference present in the heterodyne receiver by making it super heterodyne. However, this other problem called image channel interference can occur. It depends whether image channel is on air or not. If image channel is also on air, then we are getting that interference. How do we solve this issue? We have to make sure that our RF tuning circuit is rejected frequency and allowing only this one to go to the mixer. Because if the image channel reaches the mixer, there is no separation afterwards. So anything you do should be done before the mixer. That means your RF tuned circuit, RF amplifiers tuned circuit should be able to reject image channel or minimize the image channel coming into the mix. So there is a solution. That means design RF section carefully to reject the image. So remember, image channel interference is the issue with the super heterodyne receiver. Question time. If you have any doubts now, shall we discuss them? So how does image frequency come into existence in the first place? Actually, we don't know. We don't know whether the image frequency is on air or not. It may not be on air. Then we are lucky. But how do we know? Because it could be someone else transmitting a different application. So, but image is an issue created by ourselves in the super heterodyne design. So, and you know, spectrum is very populated nowadays, isn't it? It's very likely that there is somebody transmitting on this particular frequency called image. Therefore, image channel interference is like mostly present, right? You can't assume it as absent. What is another question? What is the purpose of AM detector? That is a demodulator. That demodulator is normal envelope detector, or this could be even synchronous detector. But synchronous detector is costly. So normally we put envelope detector here. That is converting that is not a conversion actually, it is extracting the envelope of the waveform and putting it into the audio amplifier. The demodulation principle which we discussed last week is being implemented here. Another question, sir, can you explain the image channel interference again? How is the unwanted frequency created? Okay, let me give an example in that case. Okay. Let's assume that my intermediate frequency I have selected, say 455 kilohertz standard value. And I want to tune to frequency band within which different AM channels will be there, like this. That is the band we will assume. Let's assume something like 200 kilohertz frequency here. Assume that out of this, I want to listen to 200 kilohertz. Sorry, 2000, right? No, 500, let's say. 500 kilohertz is my carrier. That is one I want to listen to. So what will be, I am assuming high tuning design now. So what will be my local oscillator? It will be 500 plus 455, which is FC plus FI. So 500 plus 455 is 955 kilohertz. So right now I am tuned to 955 kilohertz. Now, because 955 minus 500 will give me 455, right? Now, this value, which is FC plus 2FI, FC is 500 plus 2FI is 2 times 455, which will come to how much? 910, right? And that will be 1310, right? $1,410. Suppose 1410 megahertz channel is also there somewhere here. Some other operator or some other user is transmitting on this frequency, 1410. And 1410 is also coming here, 500 is also coming here. Let us assume that our RF tuned circuit is not very sharp, so that 1410 is also going, 500 is also going. Now what will happen? 1410 minus 955 will create the same 455 kilohertz output. Therefore, your wanted channel plus 1410 will both go into the IF amplifier, and there is no separation after that, not possible. You will have to hear or listen to both of them simultaneously, which is like heavy interference, right? So this is the issue. So if your wanted channel is 500, 1410 should not come into the mixer. Only way you can do it is you block the 1410 using the RF tuned circuit here. So the bandwidth of the RF tuned circuit should be sharp enough not to pass 1410. So your RF tuned circuit should have a bandwidth like this. It will pass all the channels that you want to tune to, but these image channels which are away from that must be removed. Image channel interference can only be removed with the proper design of the RF stage filter. Hope with that example it may be more clear, right? Okay, one more question. So is F5 frequency intermediate frequency and is given in terms of the receiver? Yes, intermediate frequency is a property of the receiver. How can the image be FC plus 2FI? What is the Fi real meaning? Is it bandwidth of the signal? No, Fi is not the bandwidth. Fi is the intermediate carrier frequency. This 455 is the intermediate carrier. So the signal you are having here is not a demodulated signal. It is a signal like this. You have both sidebands. And your carrier is now 455 kilohertz. Upper sideband, lower sideband, they are there. They will be removed by this detector. So 455 is not the bandwidth, it is the center frequency of this signal. This Fi is the center frequency, not the bandwidth. Bandwidth is fixed here. Bandwidth is only sufficient to pass the two sidebands here. It's a fixed bandwidth amplifier. Remember like this, IF amplifier or IF stage is a fixed bandwidth constant gain. Constant gain, fixed bandwidth amplifier. Constant gain, fixed bandwidth amplifier. Why? Because we want to remove the adjacent channel interference there. Another way to remember is that any image channel interference you have to remove from the RF section here using the RF section. Any adjacent channel interference you should remove in the IF section. So RF channel, image channel interference is removed by the RF section. Adjacent channel interference is removed by the IF section. Another question. So isn't the local oscillator doing the same thing as the AM detector? No. It's not a AM demodulator because the difference between these two is not audio. Previous one in the heterodyne, the difference between local oscillator frequency and the RF section was directly the baseband signal or the audio. Here, the difference is not audio, difference is an intermediate carrier. Therefore, it is not doing any demodulation. This mixer is not the demodulator. It's just down converter only. Remember this as a down converter from RF to IF. From IF to AF, we use the demodulator. Rahul is asking, sir, after the mixer, we will be getting 455 kilohertz, but the needed frequency for our need is 500 kilohertz. No, 500 kilohertz is RF. We have down converted it into 455. So our carrier is now 455, and that is the one we are going to demodulate later. So we need to listen to 500 kilohertz signal. 500 kilohertz is not the image frequency, it is the wanted frequency. Image of that frequency is 1410. This is the image. This is the wanted channel. Bandar is asking, so sir, RF part is a filter and an amplifier, not a frequency shifter. Yes, you are correct. It will not shift the frequency. It is having a small amount of amplification, barely sufficient to drive the mixer. Because most of the amplification is there in the IF, you don't want RF section to amplify heavily. Main requirement in the RF section is filtering. What filtering? Image channel should be filtered out by the RF section. Adjacent channel will go through it. That will be filtered out later in the IF section. Hope all doubts are cleared now, right? Okay, it's good that you have so many questions. I really like it. Please feel free to ask by voice also if you find the typing is difficult, right? Okay, let me erase all this now. Is it clear now, everything here? Wanted channel is called the desired channel FC. This is its image. This image must not go beyond RF. It should come here and will have to be stopped there. FC will go up to this, and whole signal is down converted to intermediate frequency, not demodulated, down converted by this. Down converted from a RF carrier to an IF carrier. Still not demodulated, sidebands will be there. This section will give a lot of amplification to the IF bandpass signal, and also it will cut off any adjacent channel interference by sharp filtering. Now, up to this point, both sidebands will be there along with the IF carrier. demodulator will remove sidebands and this audio waveform will be coming out. If it is single tone audio, only one tone will come out. And that you will amplify and listen to the tone. Dimal, one more question. Sir, does the image affect the received audio because the image carrier transmits a different audio signal? Very correct. You are very correct. Image carrier is someone else's transmission. It could be some other audio. So you will have the luxury of listening to two channels simultaneously, which you can't call luxury, right? Nobody wants that way. That is the image channel interference. Right. So with all that questions, I think it's very important that you clarify the doubts because this principle is principle to understand all kind of radio communication. Superheterodyne is the very popular receiver design, whether it's AM or FM or PM. Receiver design will use this kind of principle. Later on, at the higher semesters, you will learn there is, suppose your RF frequencies are very high, like very high in the sense, assume that it is UHF kind of frequencies, ultra high frequencies or microwave frequencies, then you will have one IF section. You may have another IF section before the demodulator. So IF1 followed by IF2. So there could be a second mixer in between these two stages. So first IF will down convert to second IF and then demodulate. That kind of design, what do you call it? You call it double superheterodyne receiving principle. Double superheterodyne receiver. So usually it is done when the frequencies of the carriers you want to tune to are in the microwave region. First IF could be usually 10.7 megahertz. Second IF is usually 455 kilohertz. Okay, give it a thought. I need 1 minute. If you have any other questions left, just yes, I think it's time for a break also. So shall we take a break of 10 minutes and meet up again? Okay, hope you are ready. We will resume. So our discussion was on the heterodyne and superheterodyne principles, which are general for AM, FM, or any other type of modulation. Right? Now we will move on to discuss different derivatives of AM, which are based on the AM principle. However, they are transmissions on their own. Right? Three versions are there. One called DSBSC, dual sideband suppressed carrier modulation. Second one, SSB, single sideband modulation. Third one called VSB, vestigial sideband modulation. Maybe in the previous semester you discussed them to some extent. Let us quickly recap. First, DSBSC, double sideband suppressed carrier. What is on screen now is our AM, generalized AM signal we derived that day, which had this carrier component plus sideband component here. And we knock off the carrier component from this signal. We remove it, leaving only the sideband component. So now our signal will be just this one is this is DSBSC, double sideband suppressed carrier. Modulated signal is the product of carrier AC cos omega CT and the signal XT here, which means we just need a multiplier. Right? Modulating signal XT multiplied by AC cos omega CT like this will produce this waveform called double sideband suppressed carrier waveform. Okay, so it will if your XT is something like this, for example, when multiplied with the carrier, you will find that this envelope being duplicated, one on the positive side, other on the other is a mirror image of that like this. There is zero crossing happening here, which is equivalent to 180-degree phase shift happening at this point. So your XT shape will be directly there in the envelope. And every time XT crosses zero, carrier will undergo 180-degree phase change, which is a phase reversal. So that's how DSBSC waveform will look like. Waiting room again. Okay. Right. Spectrum-wise, this is direct multiplication of carrier with the modulating signal. Because cos omega CT is e to the power j omega t and e to the power minus j omega t by 2, the spectrum of xt, which is xf, will be shifted by plus fc and minus fc when multiplied by e to the power component. So spectrum, this is time domain, this is frequency domain. It will be a spectrum of xt, which is capital XF, shifted by minus FC and plus FC. So Fourier transform will be like that, which when you put it to a diagram, it will be like this. So in the positive side, you have carrier here, FC, but there is no amplitude at that carrier, nothing there. Right? So because carrier is absent now, upper side band is present, lower side band is present. So that's why it's called double sideband suppressed carrier. Right? Double sidebands are present, carrier is suppressed. Why do we do this? Why are we suppressing the carrier before we are transmitting? In the AM signal, we did not suppress the carrier. We transmitted double sidebands along with the carrier. So some books will describe AM as, some books say double sideband full carrier. AM is same as double sideband full carrier. And why are we going to suppress the carrier before we transmit? We discussed the reason that day, that proportion of the transmitted power of the transmitter between carrier and the sidebands, that proportion is heavily biased. The carrier takes more than 50% of the power of the signal, even if you use highest modulation index. In single tone modulation, actually carrier takes more than 2/3 of the total power of the transmitter. Suppose your transmitter is 1 kilowatt, more than 667 watts will be on the carrier component. The remaining 1/3 is on sidebands, even if modulation index is 1. That is heavily unproportional, and carrier component is taking a lot of power, whereas it does not have any information content. To save the power of the transmitter, the best choice is you suppress the carrier, because the sidebands are now already up converted in frequency. It's in the pass band, so they can travel on their own now. Carrier component could be removed because it's taking power unnecessarily. Okay. Transmit power wise, now in a double sideband suppressed carrier signal, since there is no carrier, 100% of the transmitter power is transmitting information content. Therefore, transmit power is very efficient now. All the transmitted power is in the information bearing sidebands. Although there are two sidebands, one sideband is like replica of the other. That's a separate issue we will tackle later. But initially, sidebands are now present, carrier is absent. Therefore, we have saved a lot of power from the transmitter. Now, so DSBSC looks very good. However, we lose at the other end, the demodulation. Because now the carrier is absent in the on air, carrier is not on air, the demodulator will have to generate the carrier locally for coherent detection, because envelope detection will not work here. You saw that at every 0 crossing points, the envelope will cross. Therefore, normal envelope detector cannot be used for the DSBSC demodulation. So only choice left is now coherent detection. But you need a coherent carrier at the local oscillator, at the receiver, which means a local oscillator must be available, and it must be synchronized with the carrier of the transmitter. And that is more expensive than the simple envelope detector. Therefore, the cost of the receiver is going to be high. Okay. So transmitter's power is saved, power efficiency is good, but receiver's complexity has increasing the cost of the receiver. What do you think about that? Say broadcasting is your application. In that case, there is only one transmitter. There are thousands of receivers. So if you're going to increase the cost of receivers, some people can't afford it. Their purchasing power may not be enough. So considering that, DSBSC may not be that suitable for such applications. Right? I mean, overall economy will not be, economic requirements will not be met properly. Pereira is asking, what about the sideband splatter? The sideband splattering is the issue which you have with the AM, where modulation index is more than 1. And here there is nothing called modulation index here, because you are just multiplying the two. So there is no over modulation kind of thing. So no sideband splatter happens here. One more question, Karyavasam asking, so why does envelope detection cannot be used? Is it because envelope detection cannot detect negative? Not only that, yes, envelope detection cannot detect negative also. The other thing is this issue. On the screen, you can notice this is your modulating signal now. Here, when you demodulate using envelope detector, this is the demodulated signal. Let me draw it. This red line I'm drawing is the demodulated signal. So what we are demodulating is, this part is correct, but after that, our demodulator is going positive again, this way. So your demodulated signal will be like this. This portion is gone. That is totally different signal we are demodulating. In the time domain signal itself, you can see that. So that's the reason, and we need a modulator to get the DSBSC. Since it is just multiplication, we can use this kind of an idea. Right? You take the modulating signal, you take the carrier, and you put just 4 diodes like this to achieve the multiplier. 4 diodes in the form of a ring. That's why the name ring modulator. You can see all diodes are in the form of a ring like that. This will get the job done, multiplication. So remember, whenever you need multiplication of 2 CW signals, remember the ring modulator. You can notice ring modulator is followed by a filter here, which is a band pass filter. How does the ring operate? What is the operating principle of this? One more question. So even though modulation index is not present, isn't this equivalent to modulation index of infinity? Not really. Modulation index of infinity is not possible, isn't it? Modulation index anyway in an AM signal has to be less than 1. More than 1, even AM signal will be distorted. So it is not infinity. In that case, the power also have to go to infinity. Remember the AM power equation where we have mu squared px kind of waveform. So if mu is infinity, the DSBSC signal's power will also be infinity. That's not possible, right? Okay, coming back, let us see the operating principle of this. This is RF carrier, like this. Now, when the RF carrier is positive, this side is positive and this side is negative. These two diodes, this diode is forward biased this way. The other diode is also forward biased this way. These two diodes are reverse biased. Sorry. These two diodes are reverse biased. So D1 is forward biased, D2 is forward biased, D3 and D4 are reverse biased. So whatever the signal xt coming here during that time will be passed to the other side directly, because A and B are directly connected, C and D are directly connected. So xt will go as xt onto the other side. During the other half cycle where this side becomes positive and this side becomes negative, what's happening to the diodes? Now D2 and D1 are off, D3 is on, D4 is on, which is like cross-connecting the two wires AB, two wires AC to BC, BD, so cross-connection. Direct connection is off, cross-connection is there. Cross-connection means 180-degree phase shift. So you are having xt here, you have x dash t here, which is different signal, 180-degree phase shifted. Let's see what happens during positive half of the cycle. Input will be passed. During the negative half cycle, this will be negative. Now, 180-degree phase shift due to that cross connection. So this part will appear as negative. Then it will be positive again. This part will go negative now. So like that, you can see now it's forming a new waveform, which is DSBSC. And here is that 180-degree phase shift happening at the crossover point. Now this is single tone DSBSC waveforms envelope. So that's how the ring modulator works. Very simple principle. You are using the carrier to switch on and switch off a diode matrix. During positive half cycle, D1 and D2 are on, direct connection from input to the output. During negative half cycle, D3 and D4 are on, other two are off, cross-connecting the two wires to the output. So during negative half cycle, your input will be 180-degree phase shifted when it appears at the output. Then these sharp edges are not desirable. This kind of sharp edges, you need rounding off of those sharp edges to get a smooth sine wave. And that is the purpose of this tuned circuit here. You put a tuned circuit here, which is tuned to the carrier frequency. And all the sharp edges will be gone. And it will be a carrier frequency output with DSBSC. Modulation on now. So that circuit is very popular, not only here, in other RF circuits also later in radios, you will find the ring modulator principle popularly used. These four diodes also come as a single chip, a modulator chip, just like the rectifier diodes. Right. So that is all about DSBSC. Purpose is power saving at the transmitter. Disadvantage is receivers have got complex. because they need to use now synchronous coherent detection principle, and the receiver cost is higher. Had we used AM, we could have made the receiver cost very low because envelope detection is very low cost. That's why DSBSC never became popular in broadcasting. AM remained the choice for broadcasting for a long time before FM took over. DSBSC was theoretically there, but never became a practical broadcast system. However, it's another version. The third version we are going to discuss, so the second version is SSB. Remember, there are three derivatives. One was a DSBSC, other one is SSB, third one is VSB. This is the second one now. SSB, single sideband. This became very popular, especially for long distance communication, especially for battery operated transmission systems. What's the idea here? Concept is now, if you take a DSBSC signal, two sidebands are there, but one is just a mirror image of the other. Do we really need both? Even if we have one, all the information is there. Why do we need the duplicate? So if we can knock off the duplicate sideband, we are saving another 50% of power with respect to DSBSC. For battery operated transmitters, this is ideal. We need to use minimum power necessary so that battery could be used for a long time. Like HF jungle locks that the security forces do, they carry the battery along with the SSB transmitter. The battery can last for hours, right? Whereas AM or DSBSC is power inefficient, not suitable for such applications. So first we will generate DSBSC. How do we do that? Just multiply. Take the modulating signal, take the carrier, just multiply, you get DSBSC. This is that ring modulator. Now we have both sidebands. We will filter one of them out using a band pass filter. This one is practically known as sideband suppression filter. Sideband suppression filter. Idea is that here you will have both sidebands, no carrier. And here you will have only one sideband going out. The other sideband is the band pass filter here will be having a pass band like this, so that this will be cut off. Okay, so anyway, DSBSC is necessary to generate this one because this signal is DSBSC. So that's why DSBSC theory is still useful, although it's not practically used in applications directly. Okay, spectra, very easy to understand. DSBSC spectrum is this. We already discussed that. Out of that, one will be knocked off. Any one of the two you can remove. Then this is the spectrum. So this portion is now missing. This portion, which was there earlier, now missing. So only the upper side band is present, no carrier also. This kind of a transmission we call SSB. Single sideband transmission, highly power efficient with respect to AM. Bandwidth is also half the bandwidth of AM, also half the bandwidth of DSBSC. So bandwidth is also very efficient. This became practically very popular for shortwave broadcasting between countries. Very long distance communication was done using shortwaves, shortwave frequency range, and SSB became a very popular choice. And also I mentioned that mobile communications with the battery operated equipment, like military communication, was another popular application for this. Only issue is that the frequencies were a little low, therefore the radio is of bigger size and bit heavy to carry. Battery was also a bit heavy to carry. Other than that, it's a very useful mode for communication, especially in the military operations. We now have seen that it conserves transmission bandwidth by 50%. It makes very efficient use of transmit power. However, one issue is we have difficulty of removing that unwanted sideband, because two sidebands are very close by. You need very sharp cutoff filter there. And demodulation is also difficult because you can't use envelope detection here also. You have to use the other method, coherent detection, which is a bit expensive. SSB was known to use super heterodyne receiver principle. That sideband suppression filter in SSB was very critical, because if a portion of the sideband, unwanted sideband, also goes into the SSB demodulator, it will create distortions. So especially with the low frequencies of the signal, distortion will be created. Therefore, your ideal cutoff filter should be of rectangular shape like this. Practically, this is not possible. So practically what is possible is, with certain roll-off, you will make sure that you come down to 0 here. Like that. So that you are avoiding this spectrum completely. Then there is little disadvantage that some of these frequencies, lower frequencies, are affected because their amplitudes are reduced. So SSB signals may be not that clear compared to AM or FM. Okay. So any other questions on the SSB? I think I gave you one or two applications. One is shortwave broadcasting. Other is military communications, military mobile communications, especially for the jungle operations. Long distance broadcast signals are also SSB, because they use ionosphere for the reflection, and the ionosphere is varying during the day and night, bit unreliable. Therefore, the low bandwidth signals are desirable. Wideband signals are usually getting distorted when you transmit using ionospheric waves. shortwave, this SSB signal having the smallest possible bandwidth, it's ideal for that kind of very long distance communication between countries. The substitution to this SSB was the satellite communication, which can also bridge between countries. Before satellite communication was born, SSB was the most dominant method for transoceanic kind of communications. Anything you would like to discuss other than what I mentioned? No, right? So we will move on. So you can use this for shortwave broadcasting. However, if this baseband signal is video, not audio, then we have a problem. Because for video, spectrum of a video signal, when you look at, spectrum of a video signal could be like this. These lower frequencies of the spectrum is responsible for the bigger image that appear on the screen of the TV. Whereas these higher frequency components of the baseband are responsible for making sharp edges. For example, suppose it is a house or something, right? The bigger picture of the house is in the lower frequencies, right? Higher frequencies are giving the sharpness to the edges kind of thing, right? So sharpness of the picture is dependent on the HF component. The main image is dependent on the low frequency component. Then you can guess what will happen when you have the low frequencies cut off like this. Major portion of the video signal will be cut off. So video will be heavily distorted. Therefore, for video transmission, your sideband suppression filter like this will heavily distort the video signal. That's why vestigial sideband modulation came out. It's a compromise between the SSB and double sideband. One sideband is completely passed because we need the low frequencies of that sideband. A small portion of the other sideband called the vestige means small portion of the other sideband, is also passed because those low frequencies are very crucial for us. So sideband filter is also easy to implement now because you are not having that kind of sharp cutoff requirements like SSB. This is how we do it. This time our cutoff will be planned like this. From here, it comes down to 0 in a place like this, right? Some small portion of this other sideband is also allowed. So that portion is having kind of a dual sideband within that. And these lower frequencies are more preserved. Bandwidth is now bandwidth of this portion plus this small portion called the vestige. This portion I call beta. So W plus beta, almost W, but slightly higher. This is good for video transmission. Spectrum will look like this now. This is called the vestige, this portion. Vestige, and this is the upper sideband full. This vestige. That's how the name vestigial sideband came for TV transmission. And so TV transmissions are planned like this. Your video signal modulated onto the carrier. This is the video. And this is the vestige part, small portion of the lower sideband. And then your audio will be modulated onto a subcarrier using FM. And this is a frequency modulated subcarrier. And that subcarrier is then modulated on this main VHF carrier. That's how our TV signals come. And in fact, this diagram is not our one. This is the American NTSC standard for TV transmission. Our one is like this. We are using PAL, phase alternate line standard. PAL-B is in Sri Lanka. These are the standards, main VHF carrier here called the chrominance carrier or luminance carrier. Sorry, this is luminance carrier. Then audio subcarrier here carrying FM. Chrominance subcarrier carrying the color information is here. Vestige is 1.25 megahertz. Audio subcarrier is at 6 megahertz away from the main carrier. Color subcarrier is 4.4361875 megahertz away from the main carrier. When you look at this in the spectrum analyzer, the video signal being transmitted from a TV transmitter, spectrum analyzer look like this. The spectrum, you get the vestige here. The main carrier, this one is 272, right? Yeah, this is all this will be luminance. This is color subcarrier carrying the color information. This is audio subcarrier carrying FM audio. There is another carrier in Sri Lanka which is called Telecom carrier, digital sound. That's also being carried at a high frequency, which is not shown here. Telecom carrier is somewhere here. Okay. So this is what comes to our homes as TV. All composite TV signal. Why the name composite? Because it is having a mix of black and white transmission, color information, and audio information all in one transmission. Therefore, we call it composite TV signal. So that's the vestigial sideband. It's a derivative of amplitude modulation, which is still popular in countries like ours. We will also have to switch over from this analog TV transmission to digital TV soon. In fact, we are a little bit late in our plans in Sri Lanka. We should have switched by now in the Western province. However, there were a lot of delays in the projects. So the government has just started, I think, to plan and install the digital TV transmissions. But you can see this derivative of AM component called the VSB transmission has remained very popular over decades for TV transmission in all countries. Slowly, digital TV is taking over now. Right, that's all about AM and its derivatives. Amplitude modulation and its derivatives. Then angle modulation, which consists of two modulations, actually, FM and PM. FM stands for frequency modulation, PM stands for phase modulation, both of which will modulate the information onto this component. So this will be changed to a new component, which we call instantaneous phase angle alpha, because our information is now modulated. Such a signal we call angle modulated signal, because amplitude is not modulated, it is still constant, not modulated. All the information signal is now contained in this phase angle. So there will be an angle component coming, like theta t, after modulation. According to definitions, rate of change of the instantaneous frequency is known as instantaneous angular frequency. Sorry, here rate of change of phase. This is rate of change of phase is known as, by definition, equal to instantaneous angular frequency, which is 2π times instantaneous frequency into instantaneous frequency of the carrier. So remember these words, right? Instantaneous angular frequency there. Fi instantaneous frequency. And angle modulation, PM and FM will be there. In both cases, amplitudes you are not modulating, so same amplitude remains in both cases. Frequency, sorry, angle is getting modulated. Two options, you can modulate the angle using PM, or you can modulate using FM. So that part we will discuss next Monday, right? That's what time permits today, so I'm going to stop there. Thank you very much for joining. Okay.